Okay, my name is Carl, and I'll be talking about some custom ASICs we did for the Dune project. So I know not everyone is familiar with Lawrence Berkeley National Lab, also known as Berkeley Lab. It's the most diverse of all the US national laboratories with key strengths across the gamut of scientific research. Started out as a high-energy physics laboratory, have about 3,500 employees, about 1,000 students, and 1,750 visiting researchers. And those researchers work at our national user facilities, and what that is that we have various instruments which we make available to scientists within the US and throughout the world, such as X-ray microscopes, micromachining, nanotech, that kind of thing. And so far, we've earned 14 Nobel Prizes for the work at LBL, and the most recent was in 2020 for CRISPR gene editing. So just a real fun fact before we get started. I think LBNL might be the only place you could work where you could get addressed a letter and you actually get it delivered in elements. So you could write me a letter to Carl Grace at Lawrencium, Berkelium, Californium, Americium, and these were all discovered by LBNL along with 12 other elements. The most famous is probably plutonium in 1940. And also, everyone's seen, I'm sure I'll get out of your way, this radiation trefoil thing. That was invented in LBL as well as 1946, so you're probably aware of our work. So getting back into the story, the question is, why do we study neutrinos? Well, it turns out there's a very successful theory about particles called the Standard Model, which mostly works and does a very good job making predictions, but it's not exactly right, and no one knows exactly why. And a lot of people believe neutrinos are the key. And some of the questions that are still open are the origin of matter. Why is there matter in the universe? People believe at the Big Bang equal amounts of matter and antimatter were created, and yet the universe is full of matter. Why? Maybe neutrinos are a part of that. Black holes. You know, when a black hole is created, a huge amount of neutrinos are created as well. Can we use those to actually image the forming of a black hole? Unification of forces. There are some theoretical reasons why maybe all the forces we see, like gravitation, electromagnetism, the strong and weak forces, are actually manifestations of the same force. Neutrinos may be the key to that. So what exactly is a neutrino? Well, a neutrino is a fundamental particle, meaning it's not a composite, meaning a neutrino is not made out of anything, it just is a neutrino. And it has very low mass and only interacts with the weak nuclear force and gravity. And that means it's very hard to detect. They were first postulated in 1930 by Wolfgang Pauli, and they were used by Fermi in 1932 to explain beta decay, which is where a neutron turns into a proton in an element and ejects an electron. It turns out if you measure the energy of the electron, instead of being just the amount of energy between the proton and neutron, it's actually a range of energies. And so to make that work, they invented the neutrino, and they actually discovered it in a nuclear reactor in 1956. So say we want to detect neutrinos. Well, if we want to use them for science, there's a big catch. They are extremely difficult to detect. An average neutrino can travel 60 light years through water before getting detected. So, how do you detect something like that? Well, you attack the problem from both sides. You generate an absolutely enormous number of neutrinos, and you make an incredibly dense material to detect them so that you get as many chances as possible. And that's exactly what we're doing here with Dune. We're matching the world's most intense neutrino beam with the densest detector ever created. So Dune, which stands for the Deep Underground Neutrino Experiment, is an international science collaboration currently in construction that focuses on unraveling some of the mysteries of the neutrino. And the way it works is that an intense neutrino beam is generated at Fermilab, which is a physics laboratory near Chicago, here, and then the beam is characterized in what's called the near detector, the ND. It travels 800 miles through solid rock to the far detector, which is a mile underground in the Sanford Underground Research Facility, which is an old mine. Why do we put it underground? Well, because neutrinos are so hard to detect, we need extraordinarily low noise. And if we put it a mile underground, it will be shielded from cosmic rays and that kind of thing, which could make the signal a lot noisy. So what is the far detector? Well, I told you we wanted a very dense detector medium, and in fact, one of the best is liquid argon. It's a noble liquid, which means it's chemically inert, so we don't have a bunch of chemical reactions generating noise. It's also very, very dense in that you have a lot of argon atoms when it's liquefied in a very small location, and it's super cheap, so you can make enormous detectors out of it. In fact, the far detector, here you see it's about 66 meters in the X direction and about 20 meters tall. So it's enormous. It's filled with 17,000 tons of liquid argon when it will be built. And there's going to be 4 of these in the mine. And the only problem with liquid argon is that it's really cold. In fact, its a boiling point is minus 184 degrees C. And that means if you want your electronics to be in the argon, they have to be at that temperature as well. And this is basically shows you how it works. This is called the time projection chamber. You have a neutrino event hitting some argon atom. It loosens some charge. That charge makes a track. You put the argon in a huge electric field, so the electrons are then drifted to planes of sense wires. And then these sense wires are essentially a 3D to 2D projection of the image. And then you can find tracks, and they can tell you something about the neutrinos. So we've built a prototype called Dune. This is a smaller prototype of the FAR detector. This is in the Prévost site in France at CERN. And it contains 800 metric tons of liquid argon. And you can see by the size of that little person on the staircase, kind of a scale. And the FAR detector will be so much bigger. It'll be 20 times bigger than this. And there you can see the inside. And that's all, right now, all filled with liquid argon and currently taking data as part of the Dune experiment. So why do we want to put the electronics in the cold? Well, it turns out there's 2 options. You can put the electronics outside the tanks, which is one on the left, or you can put the electronics inside the tank on the right. And it turns out that when you're reading out charge, the capacitance is what really drives the noise. And you want as low noise as possible, as you can see those neutrino interactions. And so on this graph on the left, the x-axis is the wire length, and the y-axis is the noise in terms of electrons. Room temperature is on top, and in green is liquid argon temperature. You can see as you make the wires smaller, we get about a 2x improvement in the noise. And then when we cool the electronics, we get more than another 2x. So we get a roughly 5x improvement in noise from the state of the art by putting the electronics inside the cold volume. Therefore, electronics that can operate in liquid argon are an enabling technology for Dune. So we designed an ADC to go in the FAR detector. To meet the physics goal, it needed to have 16 channels with true 12-bit resolution at 2 megasamples per second per channel, so not super fast, but it needed much lower noise than typical of a 12-bit ADC. We needed much sub-LSB noise performance. And this was a kicker. It needs to have 30 years reliability in the cold volume. And that's a problem because once the cryostat is filled with argon and closed, it's never opening again. And we want the experiment to go at least 20 years, hopefully 30 years or beyond. And it must be able to work both at room temperature for testing and at cold temperature, so that you have to have an enormous range of applications. And here's a track from an early prototype. So what are some of the challenges about cold electronics? The first one is that it's actually less reliable to operate electronics when they're cold. That's because you have a hot electron effect. Here we have the cross-section of a transistor. The kinetic energy of the electrons when they're going from the source to the drain goes up when it's cold. That means that you have more damage at the drain channel interface, which can cause substrate current, which can actually reduce your reliability. And so you can actually do studies, and this is a study, it's a very confusing plot, but the point of this plot is we have the 3 lines of the 3 different temperatures, and this is 1 over the voltage between the drain and the source. This shows that you can extend the lifetime of a transistor by reducing the electric field at the drain. And the way you do that is you make the channel longer, you make the supply lower, and similar things. So in order to build electronics for cold, you also have to deal with a huge threshold shift. The threshold changes roughly a millivolt per degree C. So if you're operating at liquid argon temperature, you're going to have more than 200 millivolt shift as you're designing. And so we dealt with that by having circuits that were extremely robust and also very programmable so that we could adjust the configuration of the chip in different temperatures. So here's a block diagram of the chip. It has 2 pipeline ADCs, which each are fed 4 different channels. We did that because each channel was relatively slow, so we put two ADCs. You can see here that we did a 3-lab collaboration with Fermilab and Brookhaven. We have Brookhaven did the front ends and one of the references. Berkeley, we did the ADC and some of the digital, and Fermilab did most of the digital core. Because we have small design teams in the labs, such a single lab design was impractical, and we really needed a way to effectively share our design data and work as a tightly integrated design team, even though we were co-located in 3 different locations around the US. And so here are some of our ways we did it. Another issue we had is that because we've all kind of grown independently of each other, the labs all have different methodologies, different tool sets, and so on, and we had to work on a custom data set. And so we were able to share using Keysight SOS all the PDK, all the schematics and layout. An example here is that Berkeley and Fermilab shared the digital design, and so we had all the RTL on SOS, and then we also had all the SDF and everything, so that when we did a change to the design, Fermilab did the physical design, we were able to do the simulation afterwards. We also cared about sharing data in very specific ways. One of the benefits of this was that even though each of the sites has different compute architectures and different security protocols, we're able to fine-tune how we shared data so that we didn't run afoul of any IP issues or any security issues. And we also were able to only bring in IPs from the other labs that are necessary for our work, and everything was encrypted all the time. So it actually worked very seamlessly. Another real benefit that we found was that it integrated with all our design tools, so that it didn't feel like a separate, separate step. It was just kind of a natural. It felt like even though we were working with colleagues in other time zones, we were able to work as a very close team. But collaboration is hard, and I'll give you one example of a screw-up we made. So in the calibration system is a big part, because I said that one of the things we're worried about with cold ADC is that as the temperature changes and the thing ages, the performance goes all over the place. So we had to have it calibrated, on-chip calibration. And I had originally put the calibration unit along with the ADC, and then a separate calibration core, which did all of the calculations of the different weights for the calibration. And then there was a miscommunication, because I had written the RTL, and some folks at Fermilab had done the synthesis and place and route, but we didn't communicate who was going to interface, who's going to simulate that interface. And so we had some issues. It turned out the prototype was fully functional, but it wasn't able to be used in the final experiment until we fixed it. And so what I said is we stored the calibration configurations here, we calculated them there, and the problem is we had some kind of a mismatch there in simulation. So we fixed it by just basically making one big blob and putting the cal units inside so that we were able to ensure that everything was simulated correctly. And we also improved and this is actually good because it really helped us improve our collaboration. Here's how we tested the chip. Here's the die photo. It was 65 nanometer CMOS, 7 by 7 roughly in size. We both tested independently. In Fermilab, they did initial bring up by just taking a board and dunking it in liquid nitrogen. We have something here at Berkeley called the cold test system, where we have a little dewar of liquid nitrogen or argon, and this cold box that we could then have a test board that goes half cold, half warm, and I'll show you that in the next slide. So this little guy, the thing in the bottom actually goes into the cold volume. We have the ADC and a daughter card. We have heating strips in the middle. They're just basically copper strips to make sure there's no condensation. And then everything above is room temperature, able to get all the data. Here's the data we got out of it. We actually got extraordinarily good noise performance here. We have 3 ADC bins at 16 bits. Remember, this is a 12-bit ADC, but we need to look at the data at 16 bits to get anything more than just a single line in the noise idle code test. And so you can see it's 0.2 LSB at 12 bits, and that's what really drove the power dissipation, was the noise here. And you can see we got 11.92 ENOB, so we actually got better performance than a commercial solution that was used in the short baseline neutrino detector, which was a kind of a pre-experiment to this one. And just to look back to how people design custom ASICs for energy physics, back in the 80s, it was kind of a hobby for physicists. They would lay out a couple transistors and do their best. In the 90s, we started getting professional, and we'd have analog teams primarily and maybe a little bit of digital on the bottom. By the 2000s, it started to look a little bit more like commercial, where we'd have coordinated analog and digital, but we kind of kept all our controls separate. And today we've kind of entered the SoC era for large physics experiments, where we have to include a lot of IP to get things done, and who knows what the future holds. So in conclusion, the cold ADC was successfully developed by a 3-lab team to instrument a time projection chamber immersed in liquid argon. Keeping a clean, synced data repository ensured we were all able to share data seamlessly, and that was a key driver of our success. The final chip met requirements, and it can be operated over 250 degrees C range, and it gives much better performance, noise performance than commercial ADCs, because that was what our driver was. And approximately 40,000 of these ADCs, reading out 640,000 wire channels, will be deployed at the Dune far detector complex, and they'll be immersed in liquid argon for the duration of the experiment. Thank you very much.